Okay. Okay. So now we are recording. Yes. So the one question is about this discussion. Yes, I will discuss it. I will discuss it. Yeah. So I will discuss it once I reach the problem. So chapter 7. So chapter 7. Although I put all the slides here, but not all the slides. Unfortunately, we could not finish the full chapter 7. So in chapter 7, you definitely need to understand or to understand the concept of a plane wave. Okay, what is a plane wave? There are three three characteristics of the plane wave. We have seen this. And there is one important thing that you need to be able to do is to get these equations from the normal Maxwell's equations. Okay, so if you remember the normal Maxwell's equations, you have those equations. Those are in vector form. Okay, those are in what is called okay, so phasor form. Sorry. So those are in phasor forms, and those are in vector forms. So so please expect that you will be asked to calculate for example, if I give you this, if I give you an electric field an electric field is along the x-axis, and then it will be I don't know, E0 cosine omega t minus kz. Okay, and then I will ask you, well, transform this equation to the phasor form. So obviously you have to write this in a phasor form, and then you get rid of exponential j omega t like we did in class, and then you get these equations. Most importantly is to get this. It is very important. I might give you a question about using Maxwell's equations. Prove that this one, for example, or this one, for example. Okay, this is a very easy, by the way, equation or proof. We did it in class. Yeah. Yes. Yeah, the vector form will be given. This is the vector form. Yeah. So the vector form. I have an example. I will have an example right now. So once I finish, I will have I think at least 4 problems to solve for chapter 6 and chapter 7, and one of them is this aspect. Okay. Okay. So so what happens is that when you do this, you obtain a complex permittivity. Okay, a complex permittivity, and a complex permittivity will be a very important discussion here is that the permittivity now becomes, when the electromagnetic wave propagates, it becomes complex, and it has one real part and it has one imaginary part. Now you can see if the medium has sigma equals 0, which is a dielectric medium, pure dielectric, so then epsilon prime is equal to 0. Okay, epsilon second is equal to 0, which means there is no component, imaginary component in the permittivity. We will see, and we have seen, by the way, in the course, the last session, the fact that I told you, prove that if you have, well, the power is proportional to the power is proportional to the magnitude. For some reason, so the power is proportional to the magnitude of the electric field. Okay, E star E. And one question, if you remember, that we covered, proved that if you have dielectric material, there is the power does not lose anything. The power that as a function of z exponential minus kz, you don't lose anything. Okay, so we will see it also, but remember this because this is very important concept. Okay, yeah. So the wave equations, if needed, I will give them to you. However, most important thing is these two ones. So what is the wave equation? The wave equation is the Laplacian of the phasor plus k squared is equal to 0. Now remember, k is equal to omega square root of mu epsilon. Omega is the frequency of the wave, or the angular frequency, mu is the permeability, and epsilon is the permittivity, electrical permittivity of the medium. Now you can see that any so the wave in general, the electric field in general, the electric field will be, let's say, E0 exponential the phasor. We are talking about the phasor E0 exponential minus or minus j k z. Okay, right? So this is the phasor of the electric field, which does not include the time. What I told you is the power is proportional to the magnitude of the electric field. Okay. So the power is proportional to the magnitude of the electric field, which means it's proportional to E star E square root. Now, what I told you in the last session, if I put the following, if k, remember, k depends on epsilon, okay? And now we have seen that epsilon can be imaginary, can be a complex number. So which means k can be a real part, can have a real part, but can have also an imaginary part. Yeah, right? Because k is equal to omega square root of mu, in general, epsilon c. And we have seen that epsilon c is an imaginary or a complex number, which means that k can be written as kr plus j k imaginary. Okay. Now, the question here is, if k is completely real, what happens to the power? Okay. What does this mean? If k is completely real, means that, if you remember, the material is completely dielectric. Okay, it's completely dielectric, and vice versa. If k is in general kr plus j k imaginary, so which means the imaginary part is not zero, what happens to the power? All what you have to do is to calculate this E star E square root. You know that A star E is equal, or E is equal to E0 exponential, let's say, minus j k z. Okay, you replace this k here, and you see if your k is this form, if your k is always independent of z, because in one of the possibilities, this will cancel with E star. So E star will cancel with E. In the other possibility, you will have the following. You will have your power is exponential of minus k emz. And this is a number, a real number, which means your power will have an exponential decay as a function of z. Okay, so just this is all what you have to do, is to take to calculate this quantity, knowing that the electric field is this, and knowing that k has a real part and imaginary part. Okay, Okay. So this is one, I wanted to mention this because this is very important to understand in propagation of waves in the medium, whether it is a pure dielectric or pure conductor. And you will see that the wave in pure conductor will be attenuated. Then we also calculated the wave velocity, okay, the speed of the wave, the wavelength, and we also calculated the intrinsic impedance, which is intrinsic impedance is in general mu over epsilon. Okay, permittivity, permeability over permittivity. Okay? This is the intrinsic impedance. Again, this will be given. And I think that's it for the moment. No, sorry. This is the last one. This one. This is very important. We will give an example. So the magnetic field is equal to 1 over the intrinsic impedance, and K, this is very important. K is the direction of the wave direction of propagation of the wave, which means if your wave is propagating along the x-axis, this should be x. Okay, so the cross product of the direction of propagation of the wave with the electric field, and electric field is minus impedance times the direction of propagation of the wave and the cross product with the magnetic field. This is very important, and we will see it in one of the examples, because the question will be, I can give you the expression, the time expression of the electric or magnetic field, and ask you first determine the wave propagation, the direction of the wave propagation. And by determining the wave propagation from the equation of the electric field or magnetic field, you will be able to determine which component is this. Is it X, Y, or well, it is I, J, or K. Okay. I think that's it for the review. Yeah. So let me just in general the equations that will be given to you. Yeah, so those are the equations. So you will be given this one, unless you might be given this one, but you might be also asked to prove it, as I mentioned. You will be given this one, and you will be given this one. Okay. Yes. So you will be given this one, but you might be, as I mentioned, you might be given or asked to calculate or to prove this, or to find this, not to prove, to find. Okay. So let's go to some questions. The first question is, if you remember, the question of the quiz. Okay. So here, a parallel capacitor of area 10 centimeters square, it's separated by 2 centimeters, has a dielectric material of 5 epsilon 0. So this is capacitor, and the question, the capacitor is powered by an AC voltage VT. The question is, find the displacement and the conduction current in the dielectric inside the capacitor. Now, we all know that inside the capacitor, the first thing is, we know that the displacement current is equal to JD, the displacement current density ds. Okay, and we know that JD is the derivative, the change of rate of the current flux density ds. Okay, and so this is and we know that the current, the conduction current, is equal to the normal current density, which comes from the motion of electrons, S. So those are two different quantities. Okay. Now inside the capacitor, we know that there is no flow of charge. So inside the capacitor, IC is equal to 0. Okay, there is no charge moving inside the capacitor, so there is no current flowing. Okay, and that's one of the reasons that the displacement current was introduced. However, the displacement current is what? Is equal to this ds dt, sorry, and we know that d is equal to epsilon, the electric field. And we know that there is an electric field. There is an electric field, and this electric field is variating. Okay. Now, so this means that the displacement current will be equal to epsilon, the variation of the electric field with respect to time, ds, and we know that the electric field is equal to, well, I will just, because the electric field is pointing in one direction, which is always perpendicular, it's always collinear with this surface. So it will become positive and negative according to the cosine, but it will be always collinear with the surface vector. Okay, so I can get rid of it, of the vector. So the electric field is equal to, what is the electric field here? How do I determine the electric field?
It is the voltage divided by the distance.
Yeah, it's voltage divided by the distance, and the distance is given. So the voltage, which is, let's say, I will call it V0 cosine omega t, which is given. Okay, and yeah, so then the displacement current will be just epsilon over d. Okay, and then the integral of this. Okay, and the integral of this is minus V0 omega sine omega t, and then the integral over ds, which is the area. So which will give me minus epsilon a over d V0 omega sine omega t, right? And this is the capacitance. You remember the capacitance of a capacitor is equal to the permittivity, the dielectric, times the area of the capacitor divided by the distance between the two parallel plates. So the displacement current will be equal to minus C V0 omega sine omega t. So this is the displacement current, and of course in region 1 IC is equal to 0, so the total will be displacement current. Now the other question was find the displacement and conduction current in the black wire, which means here in the conductor. Now the black wire is conductor. Question B. Again, I know that the conduction current is equal to ds over s, and I know that the current here, the current here. So first, let what is this current here? What is the displacement current inside the wire?
0.
Why?
Because the electric field is 0, I think.
Yeah, because it is a pure conductor. Exactly, it is pure conductor, so the electric field is 0, which means the displacement current is 0. How do I determine the current here inside the conductor? So the current inside the conductor, in the wire, so this current, okay, exactly. So the current is the current that is flowing through the capacitor, and it is equal to the capacitor voltage to the derivative of the capacitor voltage, or the rate of change of the capacitor voltage. And the capacitor voltage, we did not include anything. It's exactly the same as V0 cosine omega t. So this means that IC is equal to minus C omega V0 sine omega t. And you can see that two currents are the same because of the charge conservation. Okay, so this is one question. Any question about this? This is one of the questions you will get, maybe more developed or combined with some other concept, but this is something that you have to understand. Okay, so let's go to the next question. Again, this is the question from the quiz, because I saw that the quiz was not good. The volume charge density of a conductor, well, actually, this is the initial charge density, is 10 to the power of 3. So the initial charge, volume charge, is equal to 10 to the 3 Coulomb per cubic meters. The conductivity is given of the conductor, and the dielectric is given, constant. Okay, dielectric. At what time will the volume charge density drop by half? Now we know that volume in general is equal to the initial exponential minus tau over t over tau, and this is the relaxation time. So the relaxation time is equal to epsilon over sigma. Okay, so this is an equation that you will be given, and this gives you the flow of the charge in a material as a function of time. Okay. So we want the charge density to drop by half, which means at time equal t, the charge density becomes rho v0 over 1/2 is equal to rho v0 exponential minus t tau. And of course, we can easily see that minus t over tau will be equal to ln of 0.5, and then t will be equal to minus tau ln 0.5. We know tau because we know epsilon and we know the conductivity. Okay. Okay. What will be this time if the material was a pure conductor? Now, if the material was a pure conductor, so the first thing, if the material was a pure conductor, which means sigma over epsilon, because sigma tau is equal to epsilon over sigma. So this will give you, if the conductor was, if the material was pure conductor, okay, pure conductor, this means that exponential minus sigma t over epsilon will be very, very large. So immediately, this will go to 0. So immediately the charge density will go to 0. And this is because the conductor is always pushing the charge. Even if you put a charge inside the conductor, it will always push it out to the surface to keep the Faraday's cage, to keep the electric field inside equal to 0. So this time will be completely 0. So time is equal to 0 immediately. Any question? Okay. Okay. So let's go to another example. Okay, here. So here, this is I think we did at least 1 or 2 problems in the in class similar to this one. The electric field phasor of a uniform plane. Now I'm giving you a phasor of a uniform plane wave is given by this. So the electric field is given. Okay, 10 exponential j 0.2 z volt per meter. If the phase velocity, so the velocity is given, and the relative permeability is given, then calculate the wavelength. What is the wavelength? So the wavelength, how do I calculate the wavelength? Yeah, exactly. So the wavelength is lambda. I only see Shahd interacting, okay? 2 pi over k. And what is k? Yes, but I don't have the frequency for the moment. The frequency is coming to the second part. So I cannot use UP over F, the velocity over F. So I need to find K, and K is 0.2. K is 0.2. K is this value. is this one. Okay. So yeah, so then you can easily calculate lambda. I think lambda will be 2 pi over 0.2, and it will be 31.42 meters. So this is question 1. Question B, what is the frequency of the wave? Yes, now I can use this formula. Now I know that the lambda is equal to the speed divided by the frequency, which means the frequency is equal to the speed of the wave divided by lambda. Please, the speed of the wave is not always the speed of light. Why? Even though it is an electromagnetic wave. Can you answer this question? Why the speed of the wave is not equal to the speed of the light, even though it's an electromagnetic wave?
Because of the medium.
Okay, I did not hear. Can you just raise your... So Omar, you talked?
No, me.
Yeah, what did you say?
I said because of the medium.
Exactly. So Omar also had the same, and I think Shahad also had the same. Yes, because of the medium. Yes, very good. Yes, because of the medium. So yes, well, then the velocity we have, we are given the velocity, and we are given so velocity 1.5 10 to the power of 8, and then this is 3142, and this will give you a frequency of 4.77 megahertz. Okay, and the other question, I think, was yeah. So the other question was the relative permittivity of the medium. So the relative permittivity of the medium. Now we know that, well, first, the permittivity of the medium, the permeability of the medium is equal to mu r mu 0. Okay, so yes, well, there are several methods to do it. Let me just remind everyone that the permittivity is this. This is the permeability, and this is the permittivity. And we know that the velocity is equal in a medium is equal to mu epsilon square root, which means mu epsilon, okay, is equal to 1 over the speed, okay, squared. And we are talking about epsilon, so epsilon is equal to mu p squared. And we can also see that epsilon r is also equal to 1 over mu epsilon 0 up squared, right? Are you following? And then, of course, epsilon r is equal. What is the question? What was the question? Question is the relative permittivity of the medium. The relative permittivity is ER. Well, there are several ways. I'm just giving the lengthy way one so that you know, just to refresh your mind about this. Okay, epsilon r is equal to 1 over mu. Mu is mu r mu 0 epsilon 0 up squared, and then you can yeah, so you can just calculate. So I think mu r is given 2.4. So 2.4 times, I know that 4 pi 10 to the minus, I think 7, and epsilon 0, 885 10 to the minus 12, and then the velocity squared, which is 1.5 10 to the power of 8 squared. And I think if you do this, you get something 67. So this is the relative permittivity. Okay? Any question? The relative permittivity. Okay? Any question?
Sir, I have a quick question about the wavelength.
Yes.
Should the unit be in nanometers or just keep it in meters?
No, Yeah, just meters. This is very, very large wavelength. So why you would, I mean, 31.42 meters. I mean, yeah, well, I understand that in physics too, we are dealing with very, very short wavelength, nanometers, okay? But here, no, we are dealing with the very large, or not very large, but with the, well, yeah, with the wavelength of the order of a meter. Yeah, in physics too, we are going to a very, very small scale, which means a very high energy. Yeah. So for example, here the frequency is megahertz, 10 to the power of 6. If you remember, in photoelectric effect, we have 10 to the power of 14 hertz. So that's why we have very short wavelength. Yeah. Okay.
Thank you, sir.
Thank you. The last question will be, what is the magnetic field? Now we are given so the last question is, what is the magnetic field? And please, this is now it is asking not about the phasor, but it is asking about the complete magnetic field, the magnetic field, the vector magnetic field. Now, the first thing is which equation do you think we will use? Let me go back to the list of equations of problem 7. Which equation you will use? Okay, yes. So it's it's called the wave polarization. Well, yes, it's this equation. Yeah, very good. Yes. Yeah. So the wave. So this is what I want, but the wave polarization is given in phasor form. Okay, it is equal to 1 epsilon times the direction of propagation of the wave times E. What is the direction of propagation of this wave? I have the electric field. So the electric field, the phasor of the electric field is given by Y 10 to the power of J, yeah, J, and 0.2 Z. Okay, so what is the propagation? Okay, I have two answers, and okay, so yes, in fact, the first thing is that because I have this Z here, for sure it's along the Z axis. The wave is propagating along the Z axis. And because I have a positive number here, this means it is along the negative Z axis. Okay, negative Z axis. So if I want to represent the wave, so this is the X axis, this is the Y axis, and the Z axis is coming out of the page. Now, the electric field is going, this is the electric field. So the electric field is going upward. The wave is propagating inside the page. Okay, the wave, this is the wave. So the wave is propagating inside the page. So this means that Hz will be equal to minus 1 epsilon k minus, because it's a negative Z axis, cross E, which is cross Y, exponential J 0.2 Z. Now K cross Y, well, J, K cross Y, it gives me which? K cross Y, it gives you, what is the, oh, what is K cross Y? K is out of the page, so it is negative X. It gives you a negative X, which means 1 over epsilon X exponential J 0.Z. Now, yes, E is the impedance character. the intrinsic impedance. Intrinsic impedance. Okay. So HZ is equal to 1 epsilon. And what is epsilon? Well, we're epsilon. But sorry, here it's 10 because the electric field is 10. So now it's 10 over epsilon along the 0.2z. Now, if I want to go back to the HZ to the time domain, from the phasor domain to the time domain, of course, I have to do this, and then it will be, of course, along the x-axis, and then cosine omega t plus 0.2z, and then you can see that the wave is propagating along the negative z-axis, and epsilon and the E we can calculate it from the this equation. So epsilon is eta is, we can calculate it. So eta is equal to mu over epsilon. Okay. So eta is equal square root of mu over epsilon, and we have already calculated the mu and epsilon. So any question? The wave is inside the page. So the wave is propagating inside the page. Okay. Did you understand this? So what do you have? If I give you, let's say I give you an electric field, phasor of the electric field is equal to the x-axis exponential, well, let's say E0 exponential j 0.2 y. Okay. X, please mute x, y, and z. Z is out of the page. Can you please mute? Who is? Zaid, please mute. I'm not sure if you. Yeah.
Sorry, I was muted. It wasn't me.
Oh yeah, someone else. Okay, but you, I see that you're okay. Thank you. Okay. So let's give this situation, and I am asking the direction of the wave and the direction of H. So I know that the electric field is along the x-axis, and I know that the wave is along the negative axis, negative y. This is the wave, direction of the wave, and of course H will be 1 over eta, the direction of the wave, which is minus y, cross the electric field, which is x E0 exponential j 0.2 y. Now we know that y cross x will give me a negative x-axis, a negative z-axis, which will mean, so y cross x. If I do y cross x, I will go into the page. Okay, I am closing the bottle, so it goes into the page, which is a minus z. With this minus, it becomes plus z. So my wave is along the z-axis, 1 epsilon E0. My magnetic field is along the z-axis. So to summarize, the electric field is along the x-axis. The magnetic field is along the z-axis. Okay, magnetic field is out of the page, and the wave is along the negative. The wave propagation is along the negative y-axis. So both of the three of them are perpendicular to each other, and there is no component of E nor B along the y-axis. This is the definition of the wave plane. So one last thing I did not cover, but probably we covered it in physics 2 before, is when I give you, for example, it is also in the slide. If I give you a magnetic field that is equal cosine omega t, and I will ask you to calculate, let's say, the induced EMF in a square, for example, the induced EMF in a square of A by A. Well, all what you have to do is to apply the definition of the Faraday's law, which is minus d over dt, the integral of b ds. And since the magnetic field does not depend on the geometrical properties of the so the magnetic field depends only on time, so you can get it out of the integral, and then of course this will give you plus omega b0 sine omega t, and then times the integral ds, and this integral will give you a square, omega b0 a square sine omega t, and so on. Okay, so those are the questions that might come up in the exam. Just here in this questions, just pay attention to the direction of propagation of the wave, of the electric field, or the magnetic field, and how to put them from the equation. Okay, any question? I will stop here. I will stop recording, then I can take questions. Let me just yeah. Zaid, you want to ask a question?
Yes, sir.
Yes.
So could you go back to that final example that you just gave us, the one with the square?
This one, right?
No, the very, very last one that you gave us. The one with the magnetic field.
With the electric field, magnetic field.
Oh, no, just the magnetic field. And you told us to find the EMF.
Yeah. Yeah, okay. Well, that's why. This one.
No, it was the very, very, very last example right after this one.
Well, that was my last one.
So you did an example after this.
You did one where you gave us like a square, and then you gave us area A and A, or the parameters A and A.
Oh, maybe the slides doesn't show to us because it shows
okay, sorry. Yeah, okay. I think yes, there is a problem with the. In fact, instead of stop recording,